I believe this is the mic part. You have to put there. Oh. So you don't need to put this one here. Just put the mic there, and you can put this one in your pocket.
Okay.
Thank you. Are we ready? Okay, good afternoon, everyone. Welcome to our EECS seminar series. Today's seminar title is Challenges and Opportunities of Data Processing in the PostMoores Law Era. So our speaker today is Professor Zhang, who is a Robert Critchfield Professor in Engineering at the Ohio State University. His research interests focus on data management in computer and distributed systems. He has made a strong effort to transfer his academic research results into state-of-the-art technology to advance the design and implementation of general-purpose computing systems. He received the 2020 ACM Microarchitecture Test of Time Award for his contribution to memory architecture design. Received PhD in computer science from the University of Colorado Boulder, where he also received Distinguished Engineering Alumni Award in 2011. He received the Education Leadership Award from the Lutheran Foundation for chairing the Department of Computer Science and Engineering at Ohio State from 2006 to 2018. He is a fellow of ACM and a fellow of IEEE. So please welcome our speaker today. Please.
Thank you, Abbas, giving such a nice introduction. I'm very glad to visit University of Toledo for academic reason. And another reason, it's very nice to see the last lake I have not seen, the Five Lakes lake area, which belong to Ohio, but I have not visited. This is the last lake I visited, so I paid a visit yesterday. The Five Lakes, I have visited all the other fours. I know some of you are undergraduate students, and so the talk today, you will understand if you have taken or if you are currently taking operating system, computer architecture, data structure, and so networking, and you would understand what I'm talking about. So I'd like to tell you something about some challenges and opportunities in this very special transition time. I'm sure you know, in our field, you know what Moore's Law is. I'm going to give you some explanation. As a senior faculty member, when I give a talk, I always gave some methodology of mine to do research, since I have done research for some years, for 30 years after my PhD. So let me give you a very brief methodology of mine. Basically, we answer three questions: what, why, and how. The first one is what. We identify problems, we make a problem statement. When you do master thesis, PhD dissertation, you always has a problem statement. And then we also need to know what is the application scope and why the problem really exists. Any evidences, why it, many research, I read lots of research papers, quite a few problems are not really, do not really exist. Okay, so then the first question is about what are problems. The second one is why we want to solve that problems. Why do we want to solve the problems? Is there a need to solve the problems? So what are the best solutions? Now we need to know if this problem exists and other people already attack the problems or try to solve the problem. So we also want to ask why we want to solve the problem. Our solution disruptive means really want to make a big change or just incremental. Okay. So what are the potential impact if we make it? And then the last question we ask, how? So we have big ideas, and we know this is important, and we know the devil is in the detail. This is very important for our students, undergraduate, master, and PhD students. So when you do a research project, and you will do the detailed implementations. So what are the challenges? And do we have sufficient resources? We cannot be very ambitious, but we need to know, can we really make the project with sufficient resources? Okay. So then what are the deliverables? What are we deliver? We have new theories, we have new discoveries, we have new method, new prototypes, and where to publish, open source our software, or we can create a startup based on. So this is the question we always ask in my last 30 years of the research. There are 3 areas in our field, including ECE, including the EE part. We have 3 parts in the digital field: infrastructure, algorithms, and the data today. Okay. So what are, in details, infrastructure, we have hardware, networking, system management. For algorithms, anything we must define by algorithm, because we want to describe a task in any areas. And data, which are the input for computing and its management, how we manage the data. Okay. So we have 3 areas. No matter where you are, you claim, if we say, I'm interested in machine learning. Yes, machine learning, you have an algorithm, you have data, and we need a facility. Okay. So today, if we want to do research, we cannot do research independent in an isolated area. Here is, the best value is here, which is, do you hear me? I think suddenly,
oh, it's on still.
It is on. Yeah, okay, come back. Thank you. So the best value is really come from the 3 areas, the intersections of the 3 areas. Okay. This is the difference. When I was a PhD student, this is not. I'm working in the independent area. So let me briefly review what Moore's Law is. In 1965, Gordon Moore was a young engineer in Intel company, and he observed that the number of transistors on the chip will be increased every 18 months. Then in 1978, he revised his law, and he said every 24 months. Every 2 years, the number of transistors would increase, would be doubled. At the same time, another brilliant engineer from IBM, his name is Robert Dennard, and he observed that we can keep the power consumption constant as the number of transistors increase in the chip. That's the reason why we always say we have a free lunch time. Okay, but the good time is gone. So if we go over the history starting from 1980, actually this is even the first microprocessor was developed in 1971. Then we can see the different slope here, and we passed several stages here. And this is a real Moore's Law from 1985 to 2005. Every 2 years, we doubled. So every year, we have 52% increase. But after 2005, And we have ending of the Dennard law, and then we have to start the multi-core. We cannot just concentrate the number of transistors in single chip. And let's look at what today. Today is only 3% increase, so almost flat, almost no increase. If we really want to expect the performance, we just cannot rely on Moore's law. Moore's law is ending. So what we have done in the past, during the free lunch time. So what we have done is, I want to use the next 30 seconds to summarize what we have studied in operating system architecture class. So basically, and a programming language. Basically, we have built a simple and one-size-fits-all computing abstraction. Okay. A computing task, no matter what, is expressed by programs executed by instruction set architecture. This is what you studied in your architecture class. And a task is divided in a sequence of a standard execution time unit, time stamp. This is what you studied in the operating system class. And then also in operating system class, we're doing more programming model. Look at your cell phone, you open several apps at the same time, but with only one computing unit, because we rotate, we schedule different processes at a time. So OS assign the time unit to each task. And then the data moving up and down through this memory hierarchy. And this is what you studied in your architecture and the operating system class. So programming, how we write a program. The program is getting simpler and simpler. We are basically, I summarize what a programming language is, simple English-based language. Okay. Anyone who can write this simple language, Python, Java, come here, we solve your problems. So the program is OS and architecture independent. You don't need to know the architecture inside. For this reason, we attract billions of users on this abstraction. So today, computer science plus engineering is the center of all. All the applications rely on the infrastructure programming abstraction for their applications. Okay. So this is really under the Moore's law, because we're building layer by layer and attracting more users. At the same time, the more transistors are building high performance. We don't need to really concern about the performance in the bottom level. But Moore's law is ending. This is not a topic I'm going to talk. Anything, there's a physical limit. So the efficiency continues to become low in both power and execution because of the number of stacks or the stack layers getting deeper and deeper, okay, without the Moore's law support. So also, there's one issue. I'm going to give you details. What are the detailed problems? The current system is non-inclusive to others. For example, there are other execution patterns, SIMD, data flow, and also domain-specific. They are not included. And as Moore's law is ending, our computing ecosystem must be restructured to continue high-performance computing. If we continue to increase the performance, we must restructure the system. For those of you who are young, you have a long way to go, lots of opportunities to get involved in this great activity. So I have 4 limits for our existing system today. The first one is kernel-centric and sustainable. This is what you studied in operating system. Everything is managed by operating system today. So we have applications, devices, everything must be controlled and managed by this kernel. So all this kernel control everything. CPU is frequently interrupted, and you know this word in operating system, interrupt. As in the free lunch time, CPU is happy to be interrupted because CPU has a lot of idle cycles. But today is different. The in-memory computing and everything is in DRAM and in NVM, so that we can quickly, in a very fast mode, to feed CPU. CPU cycle is also becoming expensive. At this time, the kernel-centric model is really not sustainable. So the question we ask, can the kernel delegate some of the responsibility to execution partners? I'm going to explain what this means, execution partners. Limit 2, general purpose computing is flexible. As I said, we have attracted billions of users to use our system. Flexible, but not efficient. Okay. So this is also, if you have taken Economics 101, and this is also same problem, the conflict between fairness and efficiency. CPU, so let me get into the general purpose to the customized device. You can see CPU and a multi-core, mainstream environment, very flexible, anyone can use it. Power and performance efficiency are very low. Okay. Let's get into the next step. GPU, efficient for applications with high SIMD parallelism. For example, if you studied the machine learning and any tensor matrix related operation, TPU is very good at. But flexibility getting lower. We need a special programming, low flexibility. So if we took another device, FPGA, efficient for application defined by the hardware. Very special programming, but very low flexibility. Actually, only the ECE students know this kind of a programming. And we computer science, most of our students don't know. And even more, the ASIC, application-specific integrated circuit, very efficient for application for customized chips. If I want to accomplish something by hardware, just build a chip. So this is a really expert program with no flexibility. Okay? We have expert programming required here. So let's look at the efficiency is getting higher on this direction and the flexibility going this direction. So fairness going this direction and efficiency going this direction. Okay? We cannot, at this system, we cannot get both. So that's limit 2. Limit 3, hardware-independent algorithm design. For those of you who have taken algorithm class, this is required for CS major, and data structure. So we study the complexity of algorithm, and which is a big O notation. So what is big O notation? It is number of computing operations. We assume moving data is free. This is true. 50 years ago, when we study algorithms. But CPU cycles are cheap. Data movement is the bottleneck of computing. When you feel that why this program is so slow, it's not because of the CPU. It is because of data movement. And many algorithms have to be architecture aware. If we don't know the architecture, and we don't know, we may write a program which is not efficient on data movement. So the reason today we need architecture-aware programming. We need to know the memory hierarchy. We need to know the parallelism, and we need to understand if there are any opportunities for adding architecture for acceleration. So here is a top 500 machine today. Every year, there are twice a year in June and November, there are world organization to rank the fastest supercomputer in the world, so-called top 500. So if you look at today's top 500, and most of them have GPU acceleration now. Algorithm design, this is what we don't teach in the algorithm class. Today, any algorithm must have 3 pillars for the design. What are the 3 pillars? The traditional one, low computing complexity, low count of computation operations. Okay, this is the same. Second one's high data locality, low data movement. But we don't teach this. Next one is high parallelism. do we have a high percentage of independent operations in our algorithm design? So the best algorithm would be perfect 3 pillars, but a small group of implementation, only 3 group have this feature that are implementation independent. So hardware and software system and algorithm co-design for the 3 pillars are required. For those of you who are young, and these classes are really important for you so that when you do the software design, it is not just at a logical level. So what happens if we only have 1 or 2 pillars? This is really happens today. We may have challenges and uncertainties in the performance. So let's look at, if we have 3 pillars, we have 8 possibilities, right? So it is straight 3 zeros. We know this is a simple case. 3 ones, 3 zeros are also simple case. This is a highly inefficient algorithm. What happens if we have 1 in each? So for example, this 1 here, and 1 here, and 1 positive pillar is not sufficient. This algorithm is still inefficient. What happened? This is the efficient algorithm execution subject to, we have good complexity, high parallelism, but locality is not that good. We have some uncertainty. So the low data movement really subject to the data movement. What happens to this case? We have good locality, complexity and good locality. At least this is a highly efficient sequential algorithm. Okay. So this is a good case for sequential algorithm. What happens? We don't have good complexity, but we have a good locality, high parallelism. We have proved this is a good opportunity for us to use the devices, external device, to accelerate applications. Even the complexity is not very good. Of course, this is the best case for 111. The last limit of today's architecture and the system, non-diverse, non-inclusive environment. So today we have a CPU. This is one size fits all only. We have GPU, we have FPGA, we have ASIC. They're not part of our ecosystem. And so we do have a reason they are not, we do not include them. They're programming difference. They're using different programming environment. For example, we use CUDA, we use a Verilog for FPGA. First difference. Second difference, execution model different because the execution pattern is different. And the last one is a management difference. For example, there are no operating system for these 3 devices. No management for them. Okay, so here is my envision, what we're going to do for the PostMoores Law time, architecture and the ecosystem we need. Okay, first, acceleration by specialized devices is the only choice. If we want to improve the performance, we must introduce acceleration so that we can continue the performance improvement, because we don't have Moore's Law now. And everything on the memory is a common practice now. So in memory, NVM storage provides fast data access. Data access to local and remote DRAM and a fast local NVM. This is a common practice. We spend less and less time to go to the storage. Process control has to be decentralized. Today, everything is controlled by the kernel. Kernel-centric management is not sustainable. So the system, when we change the ecosystem, then we still welcome billions of users. But we don't want them to learn the CUDA programming. We still want them to provide very simple program. So this is flexible. And must be flexible, specialized, and inclusive is our job. Computer science, electrical engineering, our job. It's not user's job. So a comprehensive abstraction and automatic tools are needed. We have a long way to go to build such ecosystem. Let me give you two cases what we have done along this direction. KeyValue Store, and you studied this in the data structure class. And this is a commonly used storage, KeyValue Store. So why KeyValue? What's the merits of KeyValue Store? KeyValue Store are used widely in data centers. There are only three commands. One is a get to read the value, and second one to set or to write KV item, and or to delete, three operations. So we use a hash function to make this happen. Okay. We can scale the number of working nodes to a very large scale. If you want to increase the data, I increase the number of nodes here. So what are the features of KeyValue Store? Why this is so common? First, horizontally scale. For every data access, we have a direct map for each individual KV, which is very fair. No one has special privilege. I access my KV operation faster than yours. No, everyone must go through this hashing function. But we have a vertical bottleneck. Many random maps for a stream of KVs. The problem is there are no locality because we are running around in the memory. Random access. I'm going to give you details why this happens. So let's look at the case. Today, when we do a data access, for example, buying something in the Amazon, first we need to go to the network. And then the network, we do memory management. Doing KV operation, we need an indexing operation. This is the hashing function. Okay. And then get value. Okay. Today, we rely on network. So there's an open source software called the MIKA. MIKA, we measured MIKA. The group of researchers for MIKA are networking folks. So they minimize the time of the networking management. Very good. And so networking processing time and memory management. And then there's indexing time. Surprisingly, we found that indexing time so long, index operation become one of the major bottlenecks. So when we do the KV operation, Amazon, if you buy something and there is a KV operation and the lots of times used, not for the networking operation, but for the indexing operation. Okay. So let's look at what happens here. We have a query here, and then coming here, and then you need, this is the in-memory hashing function. Going to this hashing function here, and then this is random memory access. As I said, every access is equal. You don't know where the hashing function leads you because this is a random access. And then after getting the address, then we access the value here. So the index operation is in-memory hashing table access. And in your data structure class, you may have written a program for hashing function. But your hashing function may be very small, but we're talking about billions of a record here. Imagine Amazon, how many products there? So random access, what is random access in memory? This is back to your architecture class. Okay. So random access, and here is an experiment we measured. Sequential memory access. Sequential memory access means we know we get a page, and then we access the data in the same page. What is random access? Random access, this page, access once, and go to another page, run access, and then find another page. Okay. So here is for this is random two random access, and there's sequential access here, and you can see 2 random access equivalent to 7 sequential access, and 3 random access equivalent to 16 random sequential access. So I'm not, we can continue. I'm not sure this is exponential, but change very quickly. So I'm going to explain why this happens by using a slide I used in the architecture class. In the architecture class, we teach how we access the DRAM here. So this is the DRAM core, and DRAM has a row buffer, and this is a processor. I omit the cache part inside the processor. So if we want to do, for any memory access, first we need to pre-charge the DRAM core, because DRAM uses capacitor. You need to periodically charge. That's the reason why we have a low cost. This technology, for 50 years, we have not changed that technology. So the next step is the row access. A row of DRAM is a page, K to 8K. And access that page and put it in row buffer. After that, we find the cache line, because each time we have a cache miss, find the cache line, and the whole process, pre-charge, row access, and the column access for the cache line is called the DRAM latency. Okay. So then after we get the cache line, use memory bus to transfer that cache line to the processor. Then the question we ask, each time we access the DRAM, we consider, we just go to the DRAM core. No, that's not the case. We have a locality here. What is a row buffer hit? Row buffer hit means we repeat access in the same page. That's so-called a sequential access. What is a random access? Random access means each time we access to a different page. This is what happens in KeyValue Store, the hashing function. So each time we have this big hashing table, and each time we're indexing, I need this page, then I need that page, then we have the row buffer. Here is this is the row buffer miss all the time. So how do we solve that problem? We want to use the GPU to accelerate that operation. Okay. Here, index operation here. Operation is for a sequence of query. You want to do each of you want to do a KeyValue Store, and then we first batch you in a big group here. After then, we send this to massively parallel indexing GPU for the operation here, because you can do at one time to do the indexing. Okay. After getting the address, and then we fetch the data here. So we embed the GPU inside the KeyValue Store for index. Now you can see the results here. This is the MIKA, and this is the GPU accelerated. And the indexing operation is reduced. And this is also the time difference here. The blue bar, this is the throughput. The blue bar is the MIKA, and then this is the MIKA KeyValue, called the MIKA KeyValue. Millions of operations, millions of KeyValue stores here. So you can see the difference here with a different workload and different size of the key value. This is throughput, and it's up to 210. This is millions of operations per second. So after we deliver this software, MIKA KeyValue, I don't give you the details how we implement that. Then the idea, look at this. Oh, this is something we want to use. So they continue to improve the MIKA KeyValue, and then made it as a Giga KeyValue. So this one is NVIDIA pushes MIKA KeyValue, and then what they use is their persistent kernel. That's something we cannot use. And they know the inside. We don't know the insides. And then you can see that this is they use the MIKA KeyValue as a framework, and they optimize by their kernel and push it to the. Then we also found that Intel used MIKA KeyValue and just built a chip, and this really become a Giga, the Giga KeyValue. Okay, 1 billion KeyValue operations per second, okay, because they built a MIKA KeyValue on chip. Okay. And then I also realized that MIKA KeyValue is used by Huawei, and they use the FPGA KeyValue index. They want to minimize the latency, but maintain a reasonable throughput here. Okay, so let me use another 1/3 of the time, switch the gear to take another project at a high level. Today, we use the data centers. I always ask the students, what data you manage yourself? And even so the students think, oh, we manage a lot. For example, I took a picture. I manage that. No, your picture already in the cloud. So we don't manage anything today. Everything is in the data center. Email, data center. Right? So the modern data center, what are the system requirements for modern data centers? The following 4 requirements. First, large scale and distributed in-memory processing. Everything must be accessed in the memory. I'm talking about DRAM. So we do a lot of remote access. The remote access must be low latency, high throughput. User interface must be general purpose. We talk about not customized. Computing the memory resources available to user must be elastic and scalable. And security and a process protection, if we are dealing with a single node operation, which is easy to protect the security and reliability. But if we do remote, distributed ways, and the guaranteed security and protections are challenged. Okay, so that is required. Today, what's today's situation? No system today satisfies all above requirements. So this is what we want to do. We want to produce a system satisfy requirement. Okay. We start from a topic that you studied in your operating system class called RPC, Remote Procedure Call. So the remote procedure, I use a word globalization. We know the globalization in economics. Globalization means look at the shirt we wear. It's not made in US. It's made somewhere, and globalization in foreign countries. And they rely on our products. We rely on others' products. So remote procedure call was started 1984. The idea is very simple. It said make procedure call just like a local ones. And in our programming 101 class, we call a procedure, call a sorting procedure. We have a certain variables to pass that procedure and then get the result back. The RPC abstraction users hide the communication details, but this is we're going to a different node to get the task run, but the user do not know going to use communication facility. So the semantics of RPC cover large scope of computing services here. The data centers today have many microservices. A computing task outsources many RPC services from remote nodes. Okay? They are not rely on their own. And computing nodes serve to each other today. Just like I used an example. I buy the shirt from made in Vietnam, and they buy something from here. We outsource to each other. Okay? So the RPC service model expands hardware devices and accelerators here. The RPC interface is general purpose. This is very important. RPC is not something special, widely used here. And GRPC is the open source we use. GRPC is Google. G is a Google. They released 2015. And what are the merits? There's several merits. First, they support multi-programming languages, C++, Java, Python, Go, and others, which means they attract lots of users here. And support automatic serialization and deserialization of a data structure. Support efficient communication mechanism over TCP, transport layer. This is what you studied in the networking class. TCP, okay, very standard. And widely used in major data centers, and also supporting commonly used service, Raft, TensorFlow, KeyValue Store, I just introduced. Let me quote a number from Google. Every second, every second, over 10 billion RPC, remote procedure calls, in only Google data centers, every second. So what are the limits of a gRPC? Without talking about the limits, we don't need to do anything. Very high latency, because everything's over TCP under the control of the OS kernel. Memory copies between user space and the kernel space. Overhead managed by OS, lots of interacts by OS here. So there's another mechanism or the protocols called RDMA, Remote Memory Access, which is a mechanism for low latency data exchange. So allow remote access. If I'm going to your memory, I don't need to interrupt your OS, okay, without involving the OS kernels, and neither the senders or the receivers, which is very different from the TCP. Okay. Merits of the RDMA for data-intensive applications working in the user space, and there are no copies between the kernel and user space. CPU overhead to interrupt OS kernels eliminated, and low latency for data exchange between the distributed nodes, very low latency. RDMA software and its NIC being widely available in the computer systems. So today, RDMA is not something special. We started this project with eBay. The reason they started very simple, and you are working on RDMA for so long, I'm just asking you a simple question. We have our RDMA here in eBay, but we never use it. We don't know how to use it. This is really remind us we need to look into why this widely used device that cannot be used in industry. Okay. So RDMA has been used for high-performance computing application in the national lab, in the supercomputing centers. Why this happens here? So let me give you this is the networking in your networking class, and you have the mini stack. I'm only using the transport layer here. Socket, TCP, IP, and going to Ethernet, going to talk to the other node. And what is the RDMA? RDMA is bypassing this, go directly from my buffer, user buffer, to the RDMA buffer, and go directly to the next node and going directly to the memory without going through the TCP stack. Okay. And you can also see the curve. There are two curves here, TCP latency, and then there's also the RDMA curve. Only measure the latency here. So to measure the latency here, we have two representative workloads. Let's look at the first workload here. This workload here is the size of the data is hundreds of bytes to thousands of bytes, which means small size of the data. And KeyValue Store is a representative workload here. And it's quite close, the latency there. And then if you look at another set of the workload, and there's tens of thousands of bytes. And what kind of workload they are suitable, which are deep learning. For example, TensorFlow. Okay. So what are the limits of RDMA? RDMA, narrowly focused scope of data exchange. It is not a common. It is just the data exchange. I go to your memory, you come to my memory. Okay. And limited to high performance computing application. Dedicated resource usage, if we only rely on user, the scheduling, the management, very, very limited. Low latency is the first principle, which regardless of others, I just want low latency. Limit 3, inability to connect many nodes adaptively. The connection, because without OS support. Last one is we only rely on RDMA NIC. The resources is very, very limited here. So let me summarize the two GRPC merits: many connections, general purpose but small data size, high latency due to the kernel interrupts. RDMA, large data size, but the data exchange interface only, which is not a general purpose. Number of connections also limited here. Because of this, the GRPC and RDMA are run separately for their own application, even today. And particularly industry data center, they don't use RDMA. So our current, I'm not going to give you the details. So we propose a disruptive approach after 20 years of RDMA research. Thousands of papers published, RDMA, system, networking, and many areas. Always case-by-case study. RDMA KV store, RDMA R-tray, RDMA this, RDMA that. Okay. Researchers still exploring along the same direction, but that's a dead end. Okay. So the problem, it is the RDMA interface that limits the scope of users. That's the critical issue. Okay. So what we want to do is make the RDMA to play an important role in the platform of GRPC. Embed RDMA into the low-level implementation of the GRPC. This is a lot of dirty work for this. That's the reason, publishing paper reason, nobody want to do this work. So if we have this system, what are the merits? First, user scope as large as gRPC. Because the semantics, the interface is the same, taking advantage of general purpose. Number two, merits of GRPC. RDMA is transport. In the transport layer, we have a low latency data transfer. So both low latency and high throughput and scalability. We also can maintain an independent path. If you want to use the gRPC, you go on your path, or if you want to use this hybrid system here. So let me give you a big picture, and where did we start? We start from gRPC. So this is the gRPC. This is you probably have seen this in your networking class, and so this RPC interface, okay, and then followed by the memory management, thread management, connections, and endpoint. They have their own API, sorry. And this is the transport layer. Use TCP transport layer here. So what we have done is retain the interface of a gRPC, but update each component of the management for low latency, for scalability, for modularity, and also to enable the RDMA data transfer. Okay. But outside, so the goal, I talked to the EECS, I told them, I said, we want to build a system. Suddenly, your gRPC user consider, why data transfer so fast? I have anything. You don't need to change anything, because we have done something for you in the lower level. Okay, so let me ending my talk by giving you some of the summary here. So I quote this figure. I did not give this figure myself, but this is from the HP lab. And look at your, I think this is on your left side, and this is our current system. We have a CPU, we have a memory, we connect them together. We are going to, this is the future, actually already happens. We have multiple devices. We have CPU, DSP, different type of ASIC, FPGA, ARM, different type of RISC-V now, and we have a different type of architecture. They are not one size fits all. And we have an open architecture to connect all of them, and this is really memory-driven computing. Everything goes to the memory. Yeah. In fact, we have such an inclusive environment in the internet. So let's look at the history of the internet here. What's the foundation of the internet? We have a uniform resource identifier, URL, which is just a character string for data source, right? Going to a web page, we have a standard and hypertext transfer protocol, HTTP. It's content exchange among the nodes. I don't really need to know what architecture you use. Okay? We have a protocol. We also have HTML. This is a language. And we have a web browser, execution pattern. And you can run your video, you can run your text. And the first web page in the world, and after that. First web page, 1991. 1994, there were only 3,000 websites. And today, more than 1 billion websites. Why scale so massively? Because we have this inclusive environment. Okay. So today, inclusive environments support all kinds of human activities. Web pages, YouTube, Skype, WeChat, and internet shopping, everything going there. The content is very, very different. However, we have this common inclusive environment here. Actually, this idea, long time ago, 1776, by Adam Smith, you can see it. At that time, there are no pictures. Someone sent the photo. This is Adam Smith, and he wrote a book, The Wealth of the Nations. So I cut a paragraph from his book, and he said economic growth is rooted to the increasing division of labor, which is primarily related to specialization of labor force. Okay. So you consider, today you look at globalization here. Okay. So after many years, not far from here in Detroit, Harry Ford make something happen. That's a T model. And then he divided his automobile into 8,772 units, 72 units of specialized work. And then he put an assembly line. We have a focused work here and include all the specialized job. And not far away, there's the Green Village. I guess some of you have visited Green Village. And I copied the word in front of the Green Village, and it said, Ford put the wheels on the globe. It is true. Not by the invention of the automobile, but by his assembly line here. So what happens, we are in the computing specialization era, but we don't have such an assembly line yet. This is what we're going to do, you're going to do, you're young. And okay, this is my last page. Although we study lots of topics here, in computer architecture, computer system, networking, the infrastructure, we only consider two major factors. One is the throughput, and the other one is the latency. Here. So we increase the concurrent number of processes, and then we increase the throughput by parallelism, but when we reach at a certain point, when we increase the number of concurrent processes, at a certain point we reach to the peak. And then at the same time, we increase the number of concurrent processes. At the same time, the latency is also climbing up by locality, but climbing up. So an optimal system is this. If the system we deliver, that's in the peak of the throughput and the valley of the latency, that's the best system. And every generation, we want to move this curve and this curve so that we can move to another optimal point. This is what happens generation by generations. Okay. Thank you.
Thank you so much for the very interesting presentation. Questions, please.
Thank you, Dr. Zhang, for the excellent presentation and the visionary view of the high-performance computing. What's your thought on the impact of quantum computing?
Quantum computing. Okay, this is a very good question and also a very challenging question to be. In my view, the quantum computing is in a different world. It's not in this transistor-based computer world. I think that's in the physics world. That's in a totally different ecosystem. Maybe I'm conservative. I consider in this world, we still have a long way to go. We have a long potential to get a more performance and to satisfy the requirement. The most important thing is the interface user. It's not the core. We have built the interface to user, attracting, as I said, attracting billions of users. That takes 70 years. We're talking about from 1940s to up now. So building a quantum computing with attracting billions of people, I think it's non-trivial task. So that's my answer. I may be on the conservative side because I'm too senior to change another field to quantum computing. I I'm still staying in the conventional computing area. Any other questions?
Thank you. My question is, may I know your academic opinion on 3D NAND and also on system object integration? As we have seen recently, from a marketing point of view, they have gained popularity in recent years, especially 3D NAND, like most manufacturers they are using it, and also like recently by M1, which is by Apple for system object integration. So may I know your academic opinion on this? Thank you.
Okay, thank you. That's quite a specialized question. Your first question is about the 3D memory. So NVM. And that's the challenge. I think the challenge itself, it is not to the device itself. It's really the challenge to the operating system. So when I work in both architecture and the software part, so now I have thinking on both sides. On the architecture side, the people consider, look, how fast device I have produced, you must be very happy. But on the software side, people consider, I interface with the user. Users do not interface directly with the device. So the operating system already created for the NVM, for the storage, for the memory. Now, the ideal situation is I have this NVM, which is just a flat, unlimited size of the memory. We're talking about the CPU directly connect to the NVM without memory hierarchy. The current operating system is designed for the hierarchy. There's many issues there. So we're talking about a one CPU directly connect to a flat memory, persistent memory. There are many issues to consider. With the memory hierarchy, there's some efficiency there because we have locality. But for flat memory without locality, because even you have locality, we cannot exploit locality. We are talking about uniform memory access. Every memory access is the same. Do we turn down the whole memory space? There's many issues there. So the challenge to the operating system. That's the reason why we are advancing on the memory system part. And I show you the first part of the DRAM. We are still using the capacitor-based DRAM. Very low cost. Why? That must be a reason there. I hope I answer your question. Thank you. Any others? Particular questions?
Thank you very much for your excellent presentation. I was just trying to understand that towards the end you said that internet, the HTML hypertext is some kind of form of an open architecture where we can program in very simple languages. So I was just wondering, with this HTML hypertext, this kind of environment can be used for high performance computing? Or for, like, for example, if you know this complex algorithm computing, can this platform be used? Because when I was going through your lecture while you were speaking, I was wondering, so if that is HTML is a very simple English language platform, and so it satisfies your condition that we should be able to program in very simple English-like kind of language.
Right.
So that was my question. Can this particular platform be explored for high-performance computing? Thank you.
Okay. Good, very good question. And my answer is yes or no. On the yes part, the interface has been used for high-performance computing. But the high-performance computing users are really interested in knowing the low level, using the low level of the architecture. That's the interface cannot help. So they really want to use their hand to touch the cache and all the devices there. So the interface would not help. So the interface only help the users to translate your demand to the low level. So that part, we need the tools to do that translation efficiently. So the interface part, yes, we use that, HTML, the interface part, but not in the lower level. We have many more devices now. And how we translate the request, the user doesn't understand, just want get a result, get the result of a task. But then the translator understands, now you need a GPU, and then translate to a GPU program for a device. That part, we need a lot of such tools now. We don't have this kind of tools. So that part, HTML, would not help. But on the interface part, yes.
Any other questions?
Any?
Okay, so if not, let's thank our speaker once again. Thank you. Thanks a lot.
Thank you.
Thank you. Thank you.